Okay, so now that we've looked at one example of big O notation, we're going to do a couple more here. We're going to show another one. We'll do one of the third degree, and then we'll also show how we can prove something is not big O notation. But first, we're just going to get this down as a general rule. It's proven and established in your book. For any polynomial of degree n, so example, p of x is a sub n x to the n. This is the general shape of a polynomial of degree n. We know that p of x should be on the order of x to the n. Now, it's true that a polynomial of x squared is on the order of x squared. It should also be on the order of x cubed and x to the fourth and everything above that. But we generally try to find the best fit. And there are other notations, big omega, big theta, that sort of deal with other ways to measure complexity. We're mostly going to just notice in a case like this, as we should see right away in this first example, once we see this 4x cubed is on the order of, is a polynomial of degree 3, we should know that it's going to be on the order of x cubed. So we should know this is true, but it's still going to be up to us to find the witnesses c and k. Now again, there are lots of different ways to do this, lots of different pairs of c and k that will work, but we're going to go about this the same way we did the example last time, by bumping everything up in this polynomial to the highest degree. So we're going to start with 4x cubed plus 7x squared plus 12. And what we're going to do is copy that down as 4x cubed plus 7x cubed plus 12x cubed. Each term can be brought up to the highest power, and we should feel confident that the expression on the right is always going to be bigger than the expression on the left as long as x is greater than 1. Right? 7x squared and 7x cubed are the same when x equals 1. But once you get above 1, 7x cubed should be a lot bigger than 7x squared, because we could solve this inequality and show that as long as x is greater than 1, this will hold. And the same will be true for the 12x cubed versus the 12. So by bumping everything up to the same exponent, we're probably getting a higher c value than we need. But again, we just need existence of a c value. Now what that tells us is if we combine what are now like terms on the right-hand side, we get 23x cubed when x is greater than 1. Right? And certainly we can throw in the absolute values without upsetting our inequality. And that would mean that the c was 23 and the k was 1. And it really is as simple as that. Even though the concept of big O notation and some of the definitions and how it gets used and how to compute these estimates for algorithms will be a little bit complicated, at this point in time, all we really want you to do is get comfortable with this manipulation, get comfortable with this scenario so that you can effectively find the c and a k and understand that we do have big O of x cubed for any cubic polynomial. Now, we would also be able to show that an x squared polynomial was on the order of x cubed, because simply, if everything on the left here were just on the order of x squared, x cubed would automatically be bigger if we followed the same basic steps. But what we've got down here in the second example is sort of the reverse scenario. We want to show that x cubed plus 5x is in fact not on the order of x squared. Right? And this we can't actually just do quite as simply, because we're trying to prove something is false here. We want to show that it's not possible to find existence of the c and the k. Right? Now, proving existence is pretty easy, because all we have to do is find actual values. One value would suffice, one pair of values would suffice. What we have to do now is sort of argue that there's no way you could ever come up with a c and a k. And that takes a little bit more work, a little bit more of a proof, more than a demonstration. Okay, so let's think about how x cubed plus 5x should compare to cx squared. Okay, what if we let c equal x? All right, so let's say x was fixed at some value and we let c equal x. Okay, then we would have x cubed plus 5x would be compared to x times x squared, and we know that this would still be greater as long as x is greater than 0. right? Because you have an x cubed over here, you have an x cubed over here. If you start throwing in a positive 5x, no matter what x is, right, we're going to be more than x cubed. So even if we let c equal x, x cubed plus 5x will still be greater than x. Even if this 5x wasn't here, we would have equality, right? And the issue is that this has to be true whenever x gets beyond k, right? So if we pick a c value that works for a certain k, once we go beyond that k, that c value won't work anymore, right? So if we were all the way down at 100, let's say that x was 100 or k was 100, you'd have 100 cubed plus 500 over here, you'd have 100 cubed. Okay. Once you fix that c equal 100, if we go one further down to 101, this inequality will no longer hold, right? So the idea is that there is no fixed c that will keep cx squared greater than or equal to x cubed plus 5x. Once x gets bigger than c, right, we have a problem. Okay? That might be a little bit unsatisfying as an explanation, but essentially that's the best we can do with what we know at this point, sort of argue that it's not possible. Any choice that brings the c beyond x cubed, right? If you could find a c value for a certain x value that made cx squared bigger than x cubed plus 5x, once x got larger, that would no longer hold. And if you took a look at the graphs, there's no scaling. You could play around with a bunch of different constants. Even if you made c 1,000,000, right, that might seem to cover you for a while. But what happens when x becomes 1,000,001, right? Then you have 1,000,001 cubed here, and you only have 1,000,000 times 1,000,001 squared, which is less than 1,000,001 cubed. So this will always fail to remain less than this x squared function for large enough values. Okay, so this is a little bit more of an explanation than a concrete proof, but it's really the best we can do at this point. Mostly what you'll be asked to do is sort of show that things are in the right order and just sort of get used to this association. And then in an analysis of algorithms course, you'd learn a lot more about how to actually compute the number of comparisons or operations for a algorithm, and then learn about the families of functions here.